Bismillahirrahmanirrahim. Assalamu alaikum students. Last time we discussed the PV diagram of a gas and its relation with work done by the gas, and we showed that work is not a state function, heat is not a state function, only internal energy in first law of thermodynamics is a state function. Today, first my topic is internal energy, internal energy of a gas. Internal energy of a gas is my topic. You know, we define an ideal gas, and for an ideal gas, what is the definition? We say any gas which obeys PV is equal to nRT equation is ideal gas. This equation is called ideal gas equation. Sometimes we write it PV is equal to nRT, or you can write it NKT. What is the difference? P is pressure in the gas, P is volume occupied by the gas, N is number of moles in the gas, R is universal gas constant, T is absolute temperature of the gas, and you know absolute temperature means temperature in kelvins. And when you write it this way, PV is equal to nRT, you are expressing the amount of gas in terms of number of moles in the gas. But if you write it PV is equal to nKT, then you are expressing amount of the gas in terms of number of molecules in the gas. So here capital N is number of molecules in the gas. And K is another constant. It is called Boltzmann constant, right? So you can write both ways this ideal gas equation. Any gas, any real gas, you know, behaves like ideal gas when it is kept at low densities, or in other words, when it is kept at high temperatures and low pressures. There is another idea how we relate temperature of a gas with the motion of molecules in the gas. We should know that you have seen this relation, must have seen this relation in your class 11th, half mv square average AV is equal to 3/2 kT, right? What's my left hand side? It is average translational kinetic energy, average translational kinetic energy of a molecule in the gas, right? Average translational kinetic energy of a molecule in the gas. And this equation says 3 by 2 is constant, K is Boltzmann constant. It says that average translational kinetic energy of a molecule in the gas is proportional to absolute temperature of the gas. That means if I have a gas, if I increase its temperature, its absolute temperature, I am actually increasing the average translational kinetic energy of molecules of the gas. So it relates the absolute temperature of the gas with average translational kinetic energy of its molecules, right? If I have to write the total average translational kinetic energy of the gas, I write it this way: E subscript K is equal to N half M V square average. M is mass of molecule, V is its speed, right? N is total number of molecules in the gas. So this EK is simply what? It is total translational kinetic energy of capital N number of molecules of the gas, and I can write it in terms of number of moles. I can write it 3 by 2 NKT, because 3 by 2 KT is average translational kinetic energy of one molecule. So total average translational kinetic energy of N, capital N number of molecules will be N times the value of each molecule. So you can write it 3 by 2 NKT, or I can write it 3 by 2 NRT. When you are writing it 3 by 2 NKT, this capital N is number of molecules in the gas and K is Boltzmann constant. When you write it 3 by 2 nRT, then the small n is number of moles in the gas, R is universal gas constant, T is absolute temperature in the or of the gas. So EK is what? Total translational kinetic energy of the gas. Total, I specify it, total translational kinetic energy of the gas, right? So you need to remember this, that when we talk of an ideal gas, we say its molecules are only translating. That means this is my space, X, Y, and Z. We say a molecule in an ideal gas can move along x-axis with velocity Vx. It can move along y-axis with velocity Vy, and it can move along z-axis with velocity Vz. So it is translating along 3 space axes, right? Then coming to today's topic, there is another result. You can write for an ideal gas, PV is 2/3 of EK. need to remember it. That is, the product of pressure and volume of the gas is 2/3 of total translational kinetic energy of the gas, right? And if you combine it with, as I said, that EK is 3/2 nRT, how we get there? We can get that this way also. PV is nRT also. So if I combine these two, this and this, I can write total translational kinetic energy of an ideal gas is 3/2 nRT. I've already written this. Total translational kinetic energy of an ideal gas is 3/2 nRT. So translational kinetic energy per mole of an ideal gas is 3/2 RT if small n is 1. Or you can say translational kinetic energy per molecule is 3/2 kT if you take capital N 1, right? Now, if we take this translational kinetic energy of an ideal gas as its internal energy, right? I'm saying we take this translational kinetic energy of an ideal gas as its internal energy. So we write U. What is U? Internal energy of an ideal gas. And you write U is 3/2 nRT. 3/2 nRT. So R is universal gas constant, N is number of moles in the gas, T is absolute temperature, temperature in kelvins. So that means if I have an ideal gas, I fix its amount, that is N, R is constant, then its internal energy is proportional to absolute temperature. Or in other words, it is function of temperature only. That means for an ideal gas, if you change its volume or pressure, keeping its temperature constant, its internal energy will not change because it is function of temperature only. So you need to remember this. For an ideal gas, for an ideal gas, in addition to PV is equal to nRT, its internal energy is function of its absolute temperature only. That means if I make change in internal energy of an ideal gas, its temperature, absolute temperature will change, right? Or if I make change in its temperature, its internal energy will change, right? So first we said, what is the definition of ideal gas? Now we are putting an additional restriction on the definition of an ideal gas, that we are saying that its internal energy is function of only temperature. right? Next topic, heat capacities of an ideal gas. So next topic is heat capacities of an ideal gas. Remember the definition and symbol. Heat capacity we denote by capital C, and its definition is what? Amount of heat required to raise the temperature of a body through 1 degree Celsius, right? So if the heat capacity of a system is large, of some body is large, then it is harder to heat it because you need to put a lot of heat to increase its temperature. And we have already said that we have two kinds of heat capacities. If it is my heat capacity, we write C subscript P for heat capacity at constant pressure. Heat capacity at constant pressure. That means when you are putting heat into the system, keeping its pressure constant. Then we have C subscript V, which is heat capacity at constant volume. That is, when we are putting heat into a system, keeping its volume constant. So remember it, right? Now, we know first law of thermodynamics. We write it dq is dw plus du. Plus dq, heat put into the system, plus dw, work done by the system on the surroundings. What is du? Change in internal energy of the system. So we have already discussed this result. We said that it is actually the statement of conservation of energy. It says if I am putting some heat into the system, it will be partly used by the system in doing work on its surroundings and partly in increasing its internal energy. Now consider an ideal gas. So consider an ideal gas. He said its internal energy is function of absolute temperature only, right? So if I have an ideal gas, this is my ideal gas in certain container, I have ideal gas. I'm heating it, right? I'm putting heat into this ideal gas, right? If I am heating it at constant pressure, right? If I'm heating it at constant pressure, my first law says dq is equal to dw plus du. Now the heat which I put into it will be partly used by the system in doing work on the surroundings, and part of it will go in increasing its internal energy. And since its internal energy is function of temperature, that means the part which is going into the enhancement of internal energy will lead to increase in temperature. That means at constant pressure, when I am heating an ideal gas, only portion of the heat which I am putting into the gas will go in increasing its temperature, absolute temperature. The other part will be used by the gas in doing work on its surroundings. But now compare this situation. If I am putting the heat into the same gas but at constant volume, remember, at constant volume, work done by an ideal gas is zero. Because if volume is fixed, piston is fixed, gas can do no work on its surroundings, right? That means at constant volume, all the heat which I put into the system, into this ideal gas, will go in increasing its internal energy and hence its absolute temperature, right? I repeat, at constant volume, work done by the ideal gas is zero. So the heat which I put, all of that will go in enhancing its internal energy and hence its absolute temperature. Therefore, what is the conclusion? At constant pressure, it will take more heat. It will take more heat, right? For an ideal gas to increase its temperature through certain amount than when I am heating it at constant volume. Because at constant volume, all of it is going in increasing internal energy and hence temperature, but at constant pressure, only portion of my heat will go in increasing internal energy. So the conclusion is Cp is greater than Cv. Remember it. So we have justified why Cp, heat capacity at constant pressure, is more than heat capacity at constant volume. Now my next step is I want to, now we know Cp is greater than Cv. That means Cp will be Cv plus something. Now what is this something? If Cp is greater than Cv, it will be greater than it by some amount. That's something, that term we want to calculate, find out. Now we will do that. Focus on the idea and think about it. Now let dq subscript v be the small amount of heat put into gas at constant volume. At constant volume. Small amount of heat put into the gas at constant volume. Now since work done is zero, therefore first law says change in internal energy is dq subscript v, right? Let this be my first. Now remember the relation Q is equal to C delta T. Already discussed this, that the amount of heat put into the system is proportional to the change in temperature of the system. This capital C is heat capacity of the system. Now using this relation, I can write CV is dq subscript V over dt. C is heat put in the system divided by temperature change in the system. Now, if dq subscript V is heat put into the system at constant volume, I can write heat capacity at constant volume is heat put into the system at constant volume over change in temperature, right? But first law says this dq subscript V is du. Therefore, I can write it du by dt, right? Let it be my second. So heat capacity at constant volume is du by dt. Now move forward. Let this color. Let dq subscript p be small amount of heat, put into a gas at constant pressure. Small amount of heat put into a gas at constant pressure, right? Now again, I can write Cp equal dqp or dt. I have simply used what? This thing. Q is equal to C delta T, right? So I can write Cp is equal to dqp or dt. Let it be my third. By using first law, first law of thermodynamics, I can add dqp is equal to du plus dw subscript p. dqp is heat put in the system at constant pressure. du is change in internal energy of the system. Here we are talking of an ideal gas. Plus dwp is what? Work done by the gas at constant pressure, right? So if I combine third and fourth, combining third and fourth, that means instead of this dqp, I will write du plus dw. So I will get what? Cp is equal to du by dt plus dw subscript p by dt, right? Du by dt plus dwp by dt. It's simple. I here written du plus dwp, and it will become du by dt plus dw subscript p by dt, right? Now what's du by dt? Cv, heat capacity at constant volume. What was that equation? This equation, second. So if I use second, I replace du by dt by Cv. So I'll write here using second. Right? So this is the relation. Cp is equal to Cv plus dwp by dt. And let us give some name to it. Let this equation be labeled as fifth. Now we said we want to find that something is this term. This term is what? Ratio of the work done by the system at constant pressure over change in temperature of the system. Now this equation holds for any system. It can be ideal gas, it can be real gas, it can be liquid or solid. For an ideal gas, it's special case for an ideal gas, we want to calculate work done at constant pressure. The work done at constant pressure is PdV. dV is the change volume. Now, for an ideal gas, PV is equal to nRT. And we differentiate this equation and write P dV plus VdP. It is VdP. Right. My pen. It is V. Pen. Let me fix it. It is VdP, right? PdV plus VdP is simply nR dt. Now, since we are want to calculate the work done at constant pressure, change in pressure is 0. At constant pressure, dP is 0. So this term will go. So I will get PdV is nR dt. PdV is nR dt. PdV is what? Work done by an ideal gas at constant pressure. So dWp is nR dt. Let this be my 6th. So using 6 in 5th, I will replace this by nR dt. So using 6 in 5th, we get what we get. First I have Cp, then I have Cv plus nR dt over dt. I will get Cp is equal to Cv plus nR. More simple. This nR dt I have substituted here. So I got Cp is Cv plus nR dt by dt. That is Cp is equal to C plus nR. What is the number equation? 7th. It's my equation 7. This equation has a name. This equation is called Mayer's relation. You need to remember it. This equation is valid for only for an ideal gas. And we know all real gases behave like ideal if they are kept at low densities or In other words, when they are kept at low pressures and high temperatures, right? The previous equation, let's say Cp is plus Cv plus Nr. That means if I have N moles of an ideal gas, then its heat capacity at constant pressure will be greater than heat capacity at constant volume by an amount Nr, right? 1 mole, if I have 1 mole, it will be greater by 1 R. If I have 2 moles, it will be greater, Cp will be greater than C by 2 R, and so on. But this equation, as I have already discussed, this equation, this color, this equation is valid for any system. Now for solids, when we heat a solid, it expands very little. Therefore, this term work done by the system at constant pressure, because it involves change in volume, solids expand little on heating, therefore change in volume is negligible, and this term is negligible. Therefore, for solids, Cp is approximately equal to Cv, right? And this approximation will also hold for liquids, right? Because they also expand little when they are heated, but compared to solids, Cp and Cv will be different, right? But for an ideal gas, there is a substantial difference between Cp and Cv, and that is indicated by this particular equation, right? I will give you homework now. Homework. Question is like this. A simple question. How many joules of heat, how many joules of heat energy are required to raise the temperature of 20 kg of water from 10 to 20 degree Celsius. Very simple. How many joules of heat energy are required to raise the temperature of 20 kg of water from 10 to 20 degree Celsius. This is all for today. Thank you. Work hard, do your homework. God bless you. Assalamu alaikum.